So in this numerical, there is a balanced star connected load. Okay. And load is given as 8 plus 6J ohms per phase. Okay. So right from the beginning, when the load is given as 8 plus 6J, it means that the load is the combination of resistive load and reactive load. This reactive load can be inductive load or capacitive load. Okay, so it is connected to 400 volt supply. Okay, now we have to calculate the line current, power factor, power, and total volt amperes. Okay, so what things are to be taken care of in this numerical? First is that, as in the case of the single phase system, in the single phase system, I have told you that whenever we are required to calculate the power and it is not given that which type of power is to be calculated, because power are of many types: average power, true power, real power, apparent power, instantaneous power, reactive power. But in our numerical, it is not given that which type of power is to be calculated. So whenever there is an ambiguity regarding which type of power is to be calculated, you have to always go for the real power. Next, what else is to be calculated? Power factor. So from the impedance triangle, which we have explained earlier in the theory, we know that the power factor is R by Z. Okay, it is the ratio of the resistance to the impedance. But what is to be taken care here is that power factor should not be left as it is. It should always be accompanied by lagging or leading component. So now let's move for the in the numerical. So first of all, line voltage is given as 400 volts. So we are required to calculate the phase voltage, which is 400 by root 3. Why we have calculated the phase voltage? Because in the previous numerical also I have told you that the load is connected to the phase only. So whenever we are required to calculate the current, we require two things: voltage and the impedance. So that's why phase voltage is calculated. Now the impedance is the under root of R square plus X square. Okay, from the impedance triangle also we know this thing. So if this is, say, impedance triangle, so this is Z, this is R, this is X. Okay, so this is Pythagoras theorem is applied. R square plus X square is equal to Z square. So we get 10. Now phase current, we know the impedance, we know the voltage. Take the ratio to get the value as 23.1 amperes. Again, we can observe here that this is balanced three-phase supply, but the angles are not mentioned here. Okay, so when angles are not mentioned in the voltage, you can avoid them in the current calculation as well. Okay, but if it is given, then you have to take care of that as well. Okay, so this is the magnitude of the phase current. Now line current and phase current are same. We know already. Power factor is R upon Z, so 8 by 10, because this is our impedance, R plus Jx. So R is our real component, X is our complex component. So this is 0.8 lagging. So how come we reach to the conclusion that it is lagging? Again, you have to note down carefully that if the reactive load is not specified, that whether it is inductive or capacitive, you have to always take it as inductive, hence power factor will be lagging. Okay, now line current is okay, power factor is okay, power and volt amperes is there. So this is our power triangle. So here it is volt amperes VI, where V and I are the phasor quantities in this single phase. Since it is three phase, so 3 is to be applied here. Okay, and this is our real power. So this is 3 VI cos phi. Phase voltage is known to us, phase current is known to us. Multiply them, multiply by 3, we get the volt amperes, and multiply by cos phi, we will get the this. This is the calculation based on the phase voltages and the phase current, although it can be done using line quantities using the formula root 3 VL IL cos phi. Okay.